Hi, we have been trying to solve for the Maxwell's equations, particularly in its potential form, and we found that they can be written in a particular way where we can evoke the idea of Green's function and try to solve for the Green's function first and then use maybe Green's identity to get to the solution for the potential. What is a Green's function, which is defined through this equation where grad squared g is 4 pi delta, and there are certain conditions which are same for with the potential. Saying all this, let's see what we have at this point of time. We have Green's second identity, which is psi grad square phi minus phi grad square psi d cube x prime over the volume equals the surface integral over the surface covering that volume psi del phi del n prime minus phi del psi del n prime dA prime. And we have the Poisson equation. Grad square phi is at this. See, remember that this psi and this phi are any two functions, and I am writing the Poisson equation, which is this, and I also have grad square g Okay, so few things here. When I write this grad square here, this grad square, when you calculate this grad square, you calculate the grad square everywhere in the volume. And after you have calculating the grad square everywhere in the volume, you get the value at the point where you want to calculate phi grad square psi and then get it in all points and add them up to get the integral. Okay. So when you do the grad square and you do the differentiations, that is with respect to running variable x. Here also this grad square differentiations are with respect to the variable x. I am just keeping it here such that you remember that. Now we'll take, or Green took a bold step here, very bold step. For the psi over there, I will use g, and for the phi over there in the Green's second identity, I will use the phi. So this phi will come from here and this g will come from there. And let's see if I use those, what happens to the Green's second identity. Psi is g. Grad square phi I can replace with minus rho by epsilon naught. So let me do that. And remember that when I try to integrate over this entire quantity, that rho has to be calculated at every position. So it's at x prime. And this entire thing is integrated over this. And the other term in the left hand side is minus. Now I have phi has to be calculated at x prime if I want to do that volume integral. And then grad square psi, which is grad square g, and I can replace it with minus 4 pi delta. That minus makes this plus 4 pi. And I get delta x minus x prime inside. So it's the left hand side of my Green's identity. What happens to the right hand side is rather simpler. I get psi, which is g. I can write just g over here. So del phi del n prime minus phi del g del n prime, right? Let us look at this term. I have a delta function integration over x prime, which leaves me with a phi as a function of x once I have done that integration. So I get phi as a function of x, which is what I want, the solution of the Poisson equation. I have that multiplied with 4 pi, but the 4 pi I can bring in. I can divide everything by 4 pi, so that is gone. This term I bring in the right hand side, so that minus becomes plus now. And remember, I have 1 by 4 pi, and I took the epsilon naught also outside, so I get 1 by 4 pi epsilon naught, and I am left with g xx prime times rho x prime d cube x prime. So it's a volume integral plus I have this entire thing, and remember that 1 by 4 pi. So I have this surface integral right? Left hand side is the solution we wanted. In the right hand side, let's see what we have. We have a volume term with rho, which has to be known everywhere in the volume, and I have a surface term which has phi and del phi del n prime. So some properties of the phi, this the potential, if you wish, has to be known at the surface, and I need to know what is rho at the volume. What else I need to know? We also need to know solution for g. So if you know g, the Green's function, if you know rho everywhere inside the volume, and if you know some properties of phi on the volume as painted on the surface of the volume, we will be able to write down what is the solution for the Poisson's equation. Okay, this is what this expression tells you, and that's exactly what we said we wanted, or we should be able to tell. We said it here, if you remember. It is enough to know that the source property is inside a finite volume, but then we must also know that know certain informations about the field phi at the boundary of the volume, and that's exactly what we see now in terms of this expression that we have got out of Green's identity. Very nice. And let us look at now the consequence of this step by step. So look at an example. What is the example? Universe has a single point charge at x equals to say x1 of strength q. So basically I'm asking the following question. I have, let's choose some origin. There is a position x1 where I have a charge q. I ask the question that what is phi at some other position x. Is the question, right? And we already know the solution for this. Is phi at x is given by q by 4 pi epsilon naught 1 by mod x minus x1. This is what we know from our understanding of electrostatics, Coulomb's law, etc. Let us see what we get once I use this expression. Okay, so now how do I set up the problem? First I have to set up a volume. So I take the volume to be the entire universe. Well, I can do that because all I need to know inside the volume is all the charges that is inside the volume, and we know that there is only one charge which is x equals to x1 of strength q. So I can write down the rho inside the volume. It is nothing but rho 0, q, and then my delta function x minus the charge is at x1. This is rho x, remember. So what is the boundary of the volume? The boundary surface is at infinity, right? Because I have taken the entire universe as my volume. Phi at the surface and at infinity, so I should not write the infinity, and its derivatives del phi del n, these are all 0. Say phi and del phi del n are 0 at the boundary. I don't need to integrate the surface term because it's all 0 at the boundary. If I integrate 0, I'll get 0. The only thing I need is the first term. So 1 by 4 pi epsilon naught g and then rho. So what is the solution using the Green's function? Is 1 by 4 pi epsilon naught g xx prime and rho at x prime, which is q can come outside, so x prime minus x1 d cube x prime. And you know how to do the delta function integration. It will just change, so L B g with x prime change to x1. Now this should match with that if the Green's function method to work. This is just using the example and our knowledge of the field of a point charge. We can write this statement. So G, so in this particular case, see, this is a particular, very particular solution for G. It's for a single point charge. Remember that G is the solution for a single point charge. But the boundary condition is that we have chosen the volume to be the entire universe, and the boundary condition is that at the edge of the universe, which is at infinite distance from our origin, the value of G is 0. So in that particular solution for G, we call it G prime. And this I will tell you how to get to this later, but let's call it x prime instead of x1. It is 1 by mod x minus x prime. So it doesn't depend on the direction of x minus x prime. Right? Now, let's look at this a little bit. This is a very particular case that we have looked at, where I have the boundary at infinity. But let us consider the following case. If we have a finite boundary, but there is no charge outside it. There are no charges outside it. There is one charge So what is G? Okay. See, this is again a problem of electrostatics where I have grad square phi equals minus rho by epsilon naught as my equation, and rho is a point charge. And there is a finite boundary. this will be a solution of this equation, which is the equation for G. That's why I wrote G directly here instead of phi. The right hand side is a point charge. Well, there can be some scaling in the sense that the charge may not be just 4 pi epsilon naught, but something else. But let us choose that to be 4 pi epsilon naught. But then you see, in this, so what is the difference between these two cases? One is here, the other is here. In the first case, I have a point charge, but my boundary is at infinity. I have calculated the G, which is essentially the potential for that point charge, everywhere in the space. In the second case, my boundary is finite, but then still there is only one point charge. You have just chosen the boundary to be finite, which includes that point charge. The solution for the potential for these two cases should be exactly the same, because they are the same physical problem. You have one point charge in the universe in the both cases. It is just that you have chosen two different boundaries in two different cases, right? So which means that even for this case, the solution is G prime, right? Because they are just the same physical case. What if now I add in charges outside the boundary? So I choose now this case. If we have a finite boundary, okay, so let us first look at the following case. So if you have a finite boundary and no charges outside, so we have just said from there that in this particular case, the contribution, because there is no charges outside, the solution is same G prime, right? So what does it tell us about this second term, the surface term, this term? It tells us that this phi and del phi del n prime has to be 0 at the boundary if there is no charges outside that boundary. At the surface of the boundary, this charges has to be 0, because if they are not, then my solution for phi will be different from the first case. Now if they are 0, then if I consider this case, which is almost the case of the second one, but the charge density inside is different. It's not a point source anymore. Is something, some rho. So what is the solution then? The solution then is just the volume integral. And this has a very interesting implication or interpretation, if you wish. You see, what is happening here, in the previous case, we just wrote a delta function here, but and we got the solution as G. But if I don't have a delta function, which is a point charge, but a finite charge distribution, that can also be thought of as a collection of point charges. So this rho can be broken in terms of a collection of point charges. For each charge, you will get a solution for phi, and you can just add them up. And that is allowed because the Poisson equation is an equation which is a linear equation. For a linear equation, we discussed in the first lecture that if phi 1 is a solution, phi 2 is a solution, phi 1 and phi 1 plus phi 2 also has to be a solution. And that is explicitly in play in this particular case here. See, we are going step by step here. If I go back to our original discussion of what the solution of a differential equation depends on, and we listed three things here: the operator, the source, and the boundary condition. What we did in the Green's method is, first we said that we will try to find the solution for whatever boundary condition we wish, but for the same operator with a source which is a delta function source. And that is what I get the Green's function for. So I got a Green's function which is a solution of this equation where the source is replaced by a delta function. And I write down then the solution for phi in terms of what? In terms of that Green's function, the value of rho inside the volume, and the value of the boundary conditions, essentially, which are the values of phi and del phi del n prime, and at the volume, at the surface of the volume. Next, what we have got? We have got this G prime now, which is a solution for the Green's equation when I say that the boundary is at infinity. So this G prime is a solution which is 1 by mod x minus x prime. It's a solution for the Green's equation for the boundary at infinity, which means now it's not only we are solving for a point source, we are also specifying the boundary condition, which is the boundary at infinity. So G prime only depends on what? The operator. So G prime only depends on the operator. So if I change the operator to something else, then this 1 by x minus x prime, whatever is G prime, that will change. Okay. And now we have not still explored the boundary condition on phi. So let's say that what happens if we have our boundary condition on G. So some point charge inside, which essentially tells you that now we are looking at a solution for G. And other charges outside. So what will happen in this case? Well, let's see what will happen. What will be my G in this particular case? What can I tell about it? You see, there is a point charge inside. And our superposition principle tells us that I can add the contribution for the potential for individual charges, from the contribution on potential from individual charges. For the point charge inside, I know that the solution is G prime. So I should have a solution G prime for my Green's function. And then I will have another contribution which will come from all charges outside my volume. So this is the contribution from the charge inside and boundary at infinity. And this is the contribution from all charges outside the volume. Look at it carefully. Where will this information lie? Where do I have, can I have the information of all the charges outside the volume? I cannot have it on the operator because that decides on my G prime. I cannot have it on the point charge inside the volume because that also decides what is G prime. So this information must be in the boundary condition in with G. Remember, I said boundary condition on G, not G prime. G prime boundary condition is that the boundary is at infinity. Okay, so now what is the equation for F? What is the equation for F? And all the solutions that I am doing is inside the volume that I can on which I can do all the measurements. So what is the equation for F in my volume? I call it my volume. Inside the volume, all the charges that is giving rise to F, they all are outside my volume. So for inside the volume, grad square F is 0. And I need a boundary condition on G. So remember, F plus G prime is G. The boundary condition is on G, that is known because I know G prime at the boundary, that can translate to a boundary condition on F. So if I use that boundary condition and grad square F equals to 0, I can solve for F now. Now you see G prime we have already gotten, so and you'll see that how we get it even if we don't have the knowledge for a single point charge potential. How will you do that? So G prime is already we have got, and F prime if we can solve given a boundary condition in G, it's solving Laplace equation instead of Poisson equation, which is a homogeneous equation, easier to solve. Then I get capital G. Once I get capital G for the problem, then all I need is to know the values of phi and del phi del n prime, and then I can use this solution for phi to get phi. I have to do this to integrals essentially. So that is Green's method of solving for the Poisson equation. Before we go any further, we have not still asked the question. Well, we have shown how to get to the solution, but is it a unique solution? So we have not asked the question, if is the solution unique? So is the solution of grad square phi equals minus rho by epsilon naught unique. Given rho is known, that is what you need to know the solution everywhere inside, or inside the volume, and phi and or del phi del n is known on the surface enclosing the volume. So this is called uniqueness. And the theorem that shows you that the solution unique is called uniqueness theorem. Now, showing this, that the solution is unique, is quite straightforward. And to do that, we go back to Green's first identity. I just remind you of it. The identity obviously cannot remember you. And this was true for any two scalar functions which are well behaved inside the volume. Okay, so I have this volume, and the way we will prove this is assuming a negative statement, which is we assume that there are two solutions inside. We assume for given rho in V and phi and or del phi del n prime in S, we have, so the solution is not unique, so we say that we have, say, two solutions. And we call them phi 1 and phi 2. So what does it mean? Hence, so we know that grad square phi 1 will satisfy minus rho by epsilon naught. Rho is given. Grad square phi 2 will also satisfy, the right hand side will again be same, minus rho by epsilon naught, because it's the same rho, it is already given. So we define u, which is a function, scalar function, is nothing but phi 1 minus phi 2. I am allowed to do that. So what is grad square u? Let's look at that. Grad square u will be grad square phi 1 minus grad square phi 2. And you will agree that the right hand side of grad square phi 1 and grad square phi 2 are both minus rho by epsilon naught. So this is 0. Okay. And now use u for both phi and psi in Green's first identity. Okay, so use u for both phi and psi in Green's first identity. This is my Green's first identity. So u grad square u is 0, so that term is not there. Here I get gradient of u dot gradient of u, so that is just gradient of u square. So let me write that down. So left hand side volume integral becomes gradient of u whole square, I should say mod square, d cube x prime. The right hand side I have the surface integral, which is psi del phi del n, and but psi and phi both are u, so this is u del n prime dA prime. Now u is known. At the boundary, what is the value of u at the boundary? Well, the solution for grad square phi 1, solution for this equation and this equation both at the boundary is same, because that's the boundary condition. So this is 0. If phi 1 is known, if phi is known at the boundary, then this is 0. Similarly, del u del n prime equals 0 at the boundary if del phi del n prime is known. Because del phi del n prime is the value of del phi del n prime at the boundary, and that boundary condition is what is given to you. So whatever you get the solution inside, at the boundary it should match. At the boundary there is no two solutions that they have same solution, because boundary condition is given. So what does that tell you? If either of these are 0, so if either phi or del phi del n prime is known at all points in the boundary. Okay, so this is either, this also is true if it's n, because 0 times 0 is also 0. This is 0. So what does it left us with? It left us with this from the Green's identity. I have the volume integral of gradient of u mod square of it d cube x prime is 0. See, the integrand here, the integrand is a perfect square. So it is greater than equals to 0 at all points. In the volume. Well, if I add all those points it has to be greater than equals to 0. And once I add them all, contributions from all the points, the total has to be 0. There is no other way other than gradient of u has to be 0 at all points inside. What does it mean? U does not change. In the volume. U doesn't change in the volume. And what is the value of the u at the boundary? U at boundary u at the boundary is this difference of phi, two solutions of phi at the boundary, which once you have given the boundary condition is 0. So it is 0 at the boundary and it doesn't change in the volume, implies that it's 0 everywhere. Right? 0 at the boundary, it cannot change inside the volume, it has to be 0 everywhere. But that is the case where u is known to be 0 at the boundary. If I know that del u del n is 0 at the boundary, so that tells you that u doesn't change in the boundary and u also doesn't change anywhere in between. So this plus the same thing, this u is constant. Constant means independent of x. So in that case, in this case, then phi 2 as a function of x can be written as phi 1 as a function of x plus some constant. Well, that's not a big calamity. It's true that in that case phi 1 is not absolutely unique, but all you always want is the gradient of the phi, because that gives me the electric field. So the electric field is unique, even though phi is not in this case. So that is what is the uniqueness of the solution. It goes by the name Uniqueness Theorem. Okay, so far what we have seen that we have found a method of solving the Poisson's equation in terms of the Green's function. We have seen how the Green's function can be estimated. We have already known a part of it because it comes only from the Laplacian operator, which is 1 by mod x minus x prime, and the other part will be fixed by fixing the boundary condition on G. So that will be a solution of grad square f equals to 0, right? But one thing we have not talked about yet are what are the types of boundary conditions that may exist to solve this. And this boundary condition, when I say boundary condition, is the boundary conditions of the original problem. That is, what are the values of phi and del phi del n prime we can expect to have, or how does the solution depends on that. So let us look at the solution for phi and discuss a little bit about different types of boundary conditions now. Let me first write down the two terms. And there is a purpose why I am writing this down again and again, because these are the things that it's better that if you have some remembrance of these things when you are doing electrodynamics or in electrostatics in this case. But if you remember these, life becomes easier. You don't need to go to a book and consult it all the time. So, first we talk about the type of boundary conditions. And this type is called Dirichlet boundary condition. And we see that the choice of the boundary condition was on G is still left on us. So in this case we choose G x prime equals to 0 at the boundary. And because it's Dirichlet boundary condition, we also call it the Dirichlet's Green's function. So I write it with a suffix d. Now what happens if GD is equals to boundary? Remember that this term sums up all the contributions at the boundary. So if GD equals to 0, the second term disappears. So my phi as a function of x is now only given by the first term of the surface integral. So you have the volume term all right, and this has become a Dirichlet Green's function now. I'm sorry. Minus 1 by 4 pi this actually gives rise to something that you have already done a lot, which is the method of images, which we'll discuss next time. So here we need to know phi at the boundary to solve this, right? So the boundary condition on the Green's function is chosen. It's chosen to be 0 at the boundary. So if we want to know what is phi, we said that we need to know some properties of the phi at the boundary to know phi inside my volume, and I need to know phi itself at the boundary. So that is called the Dirichlet boundary condition, where you need to know the field at the boundary. The second type is called the Newman condition, where we make a little complicated choice for the boundary condition on phi. Boundary condition on G, and I call it a Neumann G. So what I choose here is that del G del N at the boundary is minus 4 pi by the total surface area, which I can calculate by doing a integration over this surface only. It is this. Okay, so if I do that, let's see what I get for my phi. So this is now Neumann, and you see this Green's functions will be different. It will have a G prime part which is same whether it is Neumann or Dirichlet, but the contribution from F will be different for the two cases. Now del G del N, which I have chosen to be something, so which is this I have chosen to be something. So let us write this term first, which I don't know what is G, so that has to come out of the calculation. So that will come with a plus sign, 1 by 4n. So G Neumann times del phi del n prime. And I have this term left, which is 1 by 4 pi. See, the del G del N at the boundary is chosen to be a constant value, which I can just take out of the integral. So 4 pi by integral dA prime. So remember, I am writing this term now. Del G del N prime is taken to be constant, so that has come out of the integral. What is remain is phi dA prime inside the integral. Right? Now 4 pi obviously cancels out. And what is this thing? So it is phi integrated over the entire area of the boundary divided by the total area of the boundary. So this is kind of average value of phi over the surface. So what I get is phi as 1 by 4 pi epsilon naught plus these are all the business terms plus a constant term which is phi s. And again, it doesn't matter what this term is because it's an additive constant, and additive constant to the potential really doesn't do anything, any change to the electric field, because electric field is always a derivative of the potential. So here I need to know, to solve for this phi, so I need to know del phi del n at boundary. So for the Dirichlet condition, we need to know phi at the boundary. For Neumann condition, we need to know del phi del n at the boundary. So these are the two types of boundary conditions. There is one more called Cauchy. It's a mix of Dirichlet and Neumann. But remember that you cannot specify both Dirichlet and Neumann conditions, which is both phi and del phi del n, arbitrarily at the boundary, because that will lead to inconsistencies. So that is not possible. But you can specify phi at certain part of the boundary and del phi del n at certain other parts of the boundary. So that will be the Cauchy boundary condition. Okay. So we have almost done the entire development of this. The only one thing is still remaining, and let me spend only 5 minutes to motivate to that, is that how do I calculate, how do I know what is G prime. So we have just estimated or wrote it down from our knowledge of the potential of a point source. But if we do not know that, so first time you are trying to solve for these, you do not know that. How do you know what is G prime? So remember that G prime is a solution of this equation. This gradient is on X. This equation. And the boundary condition is at infinity. Or the boundary is at infinity. So G prime tends to 0 at infinity. Now in this case, there are certain conditions which you already know. So they are also called Dirichlets conditions, by the way, where we can say that this can be decomposed in its harmonics. So there can be a harmonic decomposition, or I can write this in terms of its Fourier transform. K is the conjugate variable to X. And the Fourier transform of capital G is small g, conveniently chosen. The delta distribution, or what we call delta function in physics, has a representation in terms of integrals, which looks like this. So what we do is we put this back into our equation for G. So let's calculate first what is grad square G prime. Well, the only thing in the right hand side of the expression for G prime in terms of this integral, the only thing that depends on X is this e to the power quantity. So the integral is on K, the gradient operation directly goes inside. I can write this as and remember that this gradient is on grad square is on X. What will I get if I do this? Every time I use the grad operation, I will get a ik out. So I will get ik mod square, which is nothing but minus k square. And then I will have, it's a nice exponential derivative, so I will have the exponential left over. So this will be minus k square times e to the power ik dot x minus x prime. So if you write the left hand side and the right hand side, both of them will have the integral. So I can put everything together in one side. From grad square G, the contribution I get is minus gk times minus k square so it is d cube k, and in the right hand side I have the exponential, obviously not right hand side, sorry. So this is common outside. What I'm doing is I'm writing the Poisson equation essentially, taking all the terms, both the terms in the left hand side. So obviously the right hand side will be then 0. So the first term is d cube k gk minus k square e to the I k x minus x prime. And the second term is the term which is the delta function term, which has 1 by 2 pi whole cube. I have already written that. D cube k, I have already written that. E to the power something, that I have already taken common. So what all is left is 1. And you can see if this integral has to be true, I should have gk equals 1 by k square. I'm sorry, it will not be 1, it will be 4 pi, because that's what I forgot. So this is 4 pi here. So gk comes out to be 4 pi by k square. Well, if I know gk, you see, now I am done, because I have this g prime integration, g prime written in terms of gk. So I can now write, so I know what is gk in terms of k. So this is just 4 pi by 2 pi whole cube volume integral over k by k square e to the I k dot x minus x prime, and that's it. So all I have to do is do this integration, which will turn out to be a little bit complex, and a complex integration. And if I do this integration, which I will not do, that is your homework, you will get this as this. You should be able to do now, given that you have gone through the mathematical physics course. But then what this integral in the right hand side be a function of, k is integrated over, it will be a function of x minus x prime, and it turns out that if you do the integration, what you get is g prime as mod x minus x prime. So that completes our formalism on the Green's function. Remember that this form of g prime, which is mod of 1 by mod of x minus x prime, is sacrosanct to the Laplacian operator. If there is any other operator, obviously it will be different. Okay, so that's it for today. We have gone through a formalism of getting the Green's function, and if you remember that along with this g prime, we'll get g, which is this g prime plus a f, which is a solution for the Poisson equation grad square f equals 0, with boundary condition on g. And we have seen that if the boundary condition for phi is known, then we'll choose the boundary condition for g such that g equals to 0 at the boundary, and accordingly we can have another type of boundary condition which we call the Neumann boundary condition. We can also have the mixed Cauchy boundary condition. But that is one part of the puzzle. The other part of the puzzle is that once I know g, so then depending on what type of boundary condition you have, you can write down the solution either in this form if it's the Neumann boundary condition, or in this form if it's the Dirichlet boundary condition.